Hi everyone, my name is Augusto. I'm from Brazil, and I'm going to talk to you about a carry-based feature store here at OLX Brasil. So what is OLX Brasil? OLX Brasil is the biggest C2C marketplace in Brazil. Okay, so we help sellers and buyers so they can find each others and trade that product. So we are helping them. We're helping buyers to get that things, and helping sellers to buy things, to sell things. Sorry. So we help those two customers. Showing some numbers, OLX Brazil has 6 million daily active users. It has 500K new ads per day and 5 million chats messages per day. So as you see, it's a really big platform. And with a big platforms come big problems. As you can see, OLX Brazil it's really common that fraudster try to make some money in our platform. They try to make some scams. They try to get in chat with people that is honest. So there are many scammers in our platform, and we try and we do things that minimize the impacts of those scammers. And how do we minimize the scam impact? How do we do that? Well, we use machine learning. We use machine learning in order to minimize scam impact. So we have many teams that know about entities. So we have the chat moderation team, we have the user moderation team, we have the ad moderation teams that know about the chat, the user, the ads, and they create machine learning models. And with those models, those models take decisions and can ban users based on their decisions. So we're gonna take a look at a specific use case. It was in chat moderation, and they needed to ban users as soon as possible in minutes based on chat behavior. So they had this 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 thing they needed, that it was our model needs features, online features, in order to generate predictions in near real time. But where do we get those features from? So where does those features come from? We must ask. Well, they needed, in some way, a transformation engine to serve features in real time. They needed something like that, and they could use it on their side. They could use something like that, a raw data, that the raw data comes to the transformation engine and does the aggregations, and then serves to the model the features that the model needs, and then generate the predictions. It could be done like that. But imagine if each model in production should replicate this infrastructure. What would it have? We would have something like this. We would have many models needing multiple times the same engine transformation engine. So this would not scale. So wouldn't it be better if we had just one transformation engine that could serve those features to the models? So they had this problem, and so they called our team the MLOps platform team. The MLOps platform team was responsible for building this unique transformation engine. And this would be the start of our feature store. We started by the transformation component of the feature store. And we know the feature store is a really complex and big component, but we started by the transformation. So we started by tackling this transformation. Now let's see a little about the conceptions of the feature store. Well, we defined that this is our definition of our feature store. It's a platform that centralizes processment, offers easy to create features, and promote reusability. And here, easy to create features was the main thing that we focused. We thought it must be really easy to data scientists to come up with new features. It should not be something really hard for them. And basically, this is the main idea of the feature store. There will be more components inside it, but the feature store should take data from multiple data sources and output features to real-time machine learning models or end-user applications. So we can have, as data source, we can have backbones, queues, we can have applications, we can have database listeners. We can have many things that serve as data source. Then this data source, the data should come into topics and transformed by a transformer engine that reads from these topics. So the data comes from this data source, then is sent to a topic, an internal topic of the feature store, and this topic of the feature store is used in order to do the transformations. And then the transformations should be sent to a data retrieval interface. Here we call it a topic too, a push topic. And we send the data to this data retrieve interface. And then from this data retrieve interface, the machine learning models and the end user applications can then retrieve data from this data retrieve interface. And this is what we called, what we designed as the push pipeline, because there are other types of pipeline. But the pipeline that we created here was a push pipeline. So also we can also have a pull batch interface that reads data from a data lake, as an example. We can also have a low latency scalable database and an API that reads from this database. And this is something that we didn't do it in this feature store, but it's something that is in the roadmap. We must also save data into the data lake. And we must also have an interface between the developer, the admin, and the data science, and the feature store. That is something that we are creating. But this is the main concept of the feature store, the end goal. Now we're going to talk about the feature store implementation. So for main concerns, where it must be easy to create features, the pricing, and the infrastructure complexity. So as a messaging system, we use Kafka. We use Kafka managed by AWS, Amazon MSK, in order to integrate with other components, with other queues, other database. We use Kafka Connect. It's a really cool system to integrate with other components. And what about the transformation? Well, the transformations is this thing. The transformation must talk with the Kafka, get raw data from this Kafka, and do the aggregations. What components should we use for the data aggregation? Well, we did a discovery with some transformation engines. I will talk about some of them here briefly, but just to be sure, this was our use case. It does not mean that this tool is bad. It's really bad. It's just that it was not as good for us. So we started with Flink. Flink was a tool for doing some aggregations. But we had some trouble with the documentation of Flink. And Flink, you must write the features in Java. So it was not really the preference of the data science. Then we went to PyFlink, where you write the features, the transformations. You write them in Python. But if PyFlink is still worse in documentation and maturity. Then we went to Kafka Streams. It was really nice for us, Kafka Stream, because it integrates with Kafka, with everything that Kafka does. But we must develop these transformations in Java, so it keeps data science away. Then we searched Faust, but false is not being developed anymore since the start of the pandemic. So the project is abandoned. So we couldn't use false. Then we went for KSQLdb. It's from Confluence, the same creator of Kafka. And we saw it as a really interesting transformation engine. And then we decided for KSQLdb. We think it's a good transformation engine. We went for it. And why we chose KSQLdb? Well, we chose it because of the ability to define transformation and aggregation as carries. This is the main feature that made us choose KSQLdb. This is the same interface that the data science already know how to use. They already know how to do a count star. They already know how to get a mean in a carry. So this is something they are already used to do. So we used KSQLdb as a transformation engine. And this was our architecture using KSQLdb. Well, the raw data comes. This RabbitMQ is not from the feature store, okay? It's from external projects, just to make clear. So the raw data comes from RabbitMQ, and this RabbitMQ talks with the connectors. They talk with the source connectors and the sink connectors. Then the sink connectors push the data into the topic. They save the data into the topic. And once in a topic here, the KSQLdb can interface with the topic and generate transformations with this data. And then he reads raw data from the topic and saves transformations in the cluster. And then the data is also sent to the sink, and from the sink, the RabbitMQ can read this data and generate features in order to the model to use it. And one nice thing here is that both the Kafka Connect and the KSQLdb can be deployed as Docker images, and then so we can deploy them using Kubernetes. Well, now I will show you an example of usage. We can create a stream to get the raw data. So here we have a topic with the data, and we create a stream that's read from this topic and define some characteristics of this stream. So here we can see the partition, the timestamp, the format of the message. We can also create a table that aggregates data. And as you can see here, we defined a 2 hours window session for this aggregation. And we are grouping by buyer. So we can do those things that we can do in carry, but we can also define time frames using KSQLdb. And also one thing, here you can see we have mean Levenstein distance text message. This is not a built-in KSQLdb function. This is a function that we created after. This is a user-defined function, so we can use user-defined functions to write functions that we need. So we wrote functions in Java, and that you can define your own SQL function. We can generate a stream that reads from these tables and saves into another topic. We can do things like that. And this is what we created as raw data. We have the raw data coming, and we get the raw data stream. This is just an example. We get the raw data stream, and with this raw data stream, we can generate multiple features, aggregations. We generated mean Levenstein distance in chats per user. We generated mean of number of characters in message per user and number of chats per user. Those are 3 examples of features that we can create using KSQLdb. And then we do a join of all those features, and we get the features at the end. Well, and how do you declare features? Well, we are just doing the calculations of the feature. How do we create the transformations, but we did not declare the features. This is the YAML file that declares the feature. And so the declaration is done using a YAML file, and we can declare, and we can declare the metadata, we can declare the topic that is using this, where this feature is, we can declare the SQL file, we can declare many things in this YAML file. And with this YAML file, the user should use our CLI, a lib that we created. And with this CLI, he can insert features as metadata in Hopsworks and create the streams that he needs in order to create the transformations later. And as some results, we have 5 million message inputs per day. We have created 8 features total. We have 1.5 million features output per day, and we have 2 models using the feature store. It's only in the beginning of the feature store, but these models, they were fraud models, and they got 300 to 400 fraudulent messages detected per day, and they reduced complaint by 22 to 26% in our platform. So now we will explain a little about the roadmap of the feature store, things that we are planning to build. We are planning to build the creation of features in batch. So we get features from the data lake, and how we create features from the data lake using a batch process. We are planning also the feature versioning and the feature governance. How do we see features that were created? How do we list features, edit and delete features? We are also planning to do the export of features into the data lake for training. So you created the feature and now you want to train features offline. You should be able to do it. And we also are planning to create a feature serving with database and API. So we might have a low latency database with an API that can serve those features that were generated. And that's it. Thank you. Any questions you can ask here?